Okay, so where we left off at the end of last class was this problem. This problem is really nice because it summarizes everything about analyzing a graph. First of all, remember the goal is we're analyzing this graph. Nx, 3x to the third minus 25x to the 4 plus 200. That's what we're analyzing given the domain of 0 to 9, including 0 and 9. Now, as we do this problem, we're looking at everything. We're looking at the x-intercept, the y-intercept, the extrema, the inflection points, increasing, decreasing, basically everything we've covered up until this point. So the hope is you've tried it, you've worked on it, you have an answer. Now we're going to see how we did. Now, I put a little star by x-intercept, and we'll talk about that in a minute. Remember, to find an x-intercept, you make y0. So if I set this function, 3x to the third minus 0.25 x to the 4 plus 200 equal to 0, that's going to be kind of hard to solve. That's going to be kind of hard to solve, but it is possible, but recommended. If I had to do this one, we could also find out when does the graph cross 0. So later on, I'm going to have to graph this thing. So I'm going to save this for later when we have a complicated function and it may be a little harder. And again, I can move it over, I can factor, I can do different things. But let's just figure out later when this graph crosses 0, which is where the x-intercepts are. So we'll hold off on that one a little bit later because we have an option of graphing to find the answer as well. And that's going to save us a bunch of time. Now, to find the y-intercept, a y-intercept is when x is 0. And that one kind of works out pretty nicely because everywhere there's an x in the original, we're going to put 0. And when we do that, we get y equals 0 minus 0 plus 200. We get y equals 200. So we find that we get 200. But remember, the y-intercept is an actual point. So the point, the answer is 0, 200. If you just give me 200, that is not a y-intercept. A y-intercept is a very specific location. That location is 0, 200. Okay, so we're going to pause there for a second. X-intercept we'll hold off on. Y-intercept is when you make x 0. We plug x into 0 into the original. Solve for y, we get 200. So yes, there's a y-intercept at 0, 200. Okay, so we'll come back to the x-intercept in just a little bit. The second thing we're going to do is extrema. And when we do extrema, those are the high and low points, potential, possible high and low points. So we're going to do stationary, we're going to do singular, and we're going to do endpoints. So stationary, we take the derivative and set it equal to 0. So the derivative will be 9x squared minus 1x to the third, derivative of 200 is 0, equal to 0. Now again, here's where the problems are going to be. Can you take the derivative? Problem number 1. Can you do the algebra? So even though you want to, you know what to do, can you do it? So if you got to this point and you were stuck, you have an algebra problem. If you got the derivative wrong, you have a derivative problem, right? So the hard part is you know what to do, but can you do it? And the algebra is going to keep coming up. And if you haven't tried it at all, you're just copying, right? So you have to try it. So here, what can I do? I can factor out an x squared, which leaves me with 9 minus x, set that equal to 0. And then if I set each piece equal to 0, x squared equals to 0, x equals 0. And if I put 9 minus x equals 0, I can add x, x equals 9. So in this process, I'll zoom in a little bit. In this process, we find that we get 2 possible points, 0 and 9. So we're going to make a table soon. 0 and 9 are 2 possible extrema. I don't know what they are. I don't know if they even are extrema, but those are 2 possible ones. Okay, so that's stationary. Singular, we look at the derivative, 9x squared minus 1x to the third, and we see, is there any number that would make this undefined? Is there any number that I could plug in that would make this undefined, which is dividing by 0? Well, dividing by 0, there's no dividing going on. There's no variable in the denominator. There's no number that I could plug in that would make this undefined. As far as singular, we have none. Then for endpoint, we go back to the domain. And the domain is 0 to 9, so it's the same points we found as the stationary. So we basically found 0 and 9. Those are endpoints, but they're also possible stationary points. Okay? So the only numbers we need to look up are 0 and 9. And we're going to plug those into the original. We're going to plug them into the original. So I'm going to go to my calculator. And let's plug in the original. Well, if I go to my calculator, we go to y equals, we plug in the original. Remember, it's all about the original. 3x raised to the third minus 0.25x raised to the 4 plus 200. Function, our original function, we're going to go to the table and plug in 0 and 9. We're going to plug in 0 and 9. So I go to second graph for the table. I plug in 0. I get 200, and I plug in 9, and I get 746.75. Okay, so those are the 2 points that I'm interested in: 0, 200, and 9, 746.75. So 0, 200, and 9, 746.75. Now, in order to figure out if those are maxes or mins, or if they're even either one of those, I'm going to have to graph it. Now, in order to graph it, I need a window. Well, to figure out the window, the domain is 0 to 9. That means I have to start at 0 and I have to end at 9. I have no choice. That's where it begins to exist. That's where it ends to exist. So I'm going to count by 1. So 1, 2, 3, 4, 5, 6, 7, 8. Then the y, I'm just going to have to look at the numbers I need. So I need 0, 200, and I need 0, 746.75. So I'm going to go from 0 to, let's say, 800. That will cover my points, and I can always change it, right? I don't have to keep that. I can make it larger, make it smaller, all I want. But the goal is to be able to see 0, 200, got it, and 9, 746, got it. I can see those 2 points. That means I got it. So now we go to the calculator, go to window. We're going to go from 0 to 9, counting by ones. And I'm going to go from 0 to 800. I counted by 200s. And I'm going to look at it. If I want to adjust the window, I totally can. I can't adjust the X's, but I can adjust the Y if needed. So I hit graph, and there's your graph. There's your graph. So it basically looks like a little, kind of like an S. Okay, and we have those 2 points. We have those 2 points. Once we have those 2 points, I can now look at them and say, is it a max or is it a min? So call out loud, is 0, 200 a max or a min? That is going to be a local min. Why is it a min? Because you got to walk down to it. You got to walk down to it. And then at 9, 746.75, what do we have there? That's a local max. Local max. Now, I'm going to pause there, see if anybody has any questions, but I'm going to go back and answer the x-intercepts. Does it have a y-intercept at 0, 200? Yep. Where does this graph cross the x-intercept? It doesn't. So that answers my question real quickly. As far as x-intercept, none. None. Okay, we'll take a little break, see if you have any questions, then we'll do inflection point. All right, so for inflection points, remember you take the derivative twice and then set equal to 0. So the first derivative is 9x squared minus x to the third. The second derivative is 18x minus 3x squared and set equal to 0. Now, at this point, algebra. You can factor out a 3x, which would leave you with 6 minus x. Set each piece equal to 0. Divided by 3, x equals 0. Add x, x equals 6. So it shows that we have two inflection points where it changes from concave up to concave down, concave up to concave down. But remember, we're looking for inflection points. So my final answer needs to be 0 comma something and 6 comma something. Okay, so we go to the table. Second graph. We already got 0 in there, and we're going to add 6. So 200 and 524. 200 and 524. Now remember, that is where it changes from concave up to concave down. Concave up to concave down. So let's go look at it. Let's go to the graph. And if we hit second trace, number one for value, and put in 0, it's a little tough to see because we don't see the area to the left, but that's where the change happens, where it must have been concave down, sad face, and then it changes to concave up. Notice we're in a concave up area. And then when you type in 6, 6 is where it changes from concave up, and then now it's concave down. Changes from happy face at 6, changes to sad face. So again, having the graph, all the answers are staring at you. All the answers are staring at you, which means, we have 2 inflection points. And then the last question for this graph isn't that bad at all. When is the graph increasing? When is the graph increasing? So let's look at the graph. When is it increasing? It's all increasing. Starting here, it only goes up. It never goes down. It's starting at a leveling off phase. So and that's a great question. Let's examine 0. So I'm going to type in 0. And from 0, I'm going to press trace. When I press trace, look at the y values. Are they going up or going down? They're going up, going up. And then even up here, look at the y values. They're still going up. It's increasing the whole time. It's at a flat point, and from that point, it's going up. So here, to answer this question, when is it increasing? It's always increasing from 0 all the way to 9. And 0 and 9 are included because the domain has it as equal to. Okay, so if I was going to give a summary, which is the whole point of analyzing a graph, what did we find? We found that x-intercept, none. We found y-intercept, where was it? 0, 200. We found a local min at 0, 200. We found a local max at 9, 7, 46, 75. And we found 2 inflection points at 0, 200 and 6, 524. And this graph is increasing from 0 to 9. So in summary, that's everything we found. And that's pretty much everything we've gone over up to this point in chapter 4. All right, so let's go ahead and start our new section. The new section is 4.5. 4.5 talks about absolute min and absolute max. Absolute min and absolute max. 4.5 talks about absolute min and absolute max, okay? So we've been saying local min, local max, local min, local max, but now we're gonna add this term of absolute. Absolute means you are the highest point in the entire graph. Absolute means you are the lowest point in the entire graph. So I'm going to just draw a picture. I'm going to draw a picture, just making it up, Okay, so there's a picture. I just totally made it up. Notice that just by looking at the graph, there are 1, 2, 3, 4, 5 extrema. Are we okay? There are 5 extrema. We're going to go through them all, and all I want you to do is tell me max or min. Max or min. The first one. Second one, max. Third one, min. Fourth one, max. And fifth one, min. So we're pretty comfortable talking about maxes or min. Now, before this point, we would say local max, local min. Now we're adding absolute. But remember, absolute means you are the highest point in the entire graph, or you are the lowest point in the entire graph. Okay, so let's go through each one again, and your choices are local or absolute. So this min is at a local or absolute. Local, it is not the lowest point in the entire graph. This max, absolute or local. Now, is it the highest max? Absolutely. But is it the highest point? No, because there's an arrow and this graph goes up forever. Is this the highest point in the entire graph? No. So this is only a local. Now you're understanding what absolute means. Absolute means the highest point or the lowest point. So what about this min, the third one? That's a local min. It's not the lowest point. What about this max? Local max. And then what about this min? This would be an absolute min. Now, why is it an absolute min? Is there any point in this entire graph that's lower than that? No, this is not an arrow. It's not going down. If it was going down, it would go down forever. This is up here. This goes up. This is the lowest point in the entire graph. Therefore, it's an absolute. So absolute is kind of reserved to being the highest point in the graph or the lowest point in the graph. It's going to be one of the extrema, but is it a local or is it an absolute? Now, speaking of extrema, let's do a little practice. So here, you already have the graph. Here is your function. I'm even going to give you a hint. Instead of putting x to the third over the 3, I'm going to put 1/3 x to the 3 minus 4x. And I just want to use this. You have the graph. You have the answer. I want you to practice find extrema. So that means I want you to do stationary, singular endpoints. There is no domain. There is no domain. You can see because the arrow goes up forever, goes down forever. You're going to make a table, and you don't have to make a graph because the graph is already provided to you. Normally, of course, we make our own graph, but this is going to be like a little warm-up to see how you're doing. But will that little fraction mess you up? Will the algebra mess you up? That's the concerns I have. It's not about learning it. All of you got it. It's, can you do it? So to find stationary, take the derivative. 3 times a third is 1. So that's going to be x squared minus 4 equals 0. When you work that out, please be careful. Plus 4 plus 4. When you get x squared equals 4, what do you get for x? Plus or minus 2. You get 2 answers. So if you only have the positive, you're missing one. So we have -2 and 2. Then singular, if you look at the derivative, is there anything dividing? Is there anything we have to worry about? None. And were we given a domain? None. Now, here's where I want to point out a few things. You were given the graph. Normally you won't, but you're given the graph. So before you even touch this problem, you can see 1, 2. There's 2 extrema just by looking at it. So if you did the algebra and only got 2, you're going to miss an entire other point that's staring at you, right? So use the graph to figure that out. Then if we go to the calculator, plug in -2 and 2, we get 1/3, and even that changing to 1/3, that's going to throw some people off. X raised to the 3 minus 4x second table, -2 gives you 5 1/3, and 2 gives you -5 1/3. So we get 5 1/3, we get -5 1/3. We can verify -2, 5 1/3. What do we have here? Max or min? Max, local or absolute? Local, because the graph goes up forever. And then what do we have at 2, max or min? Min, local or absolute? Local as well, because the graph lets you goes down forever. Okay, now we're going to throw in, just for a little extra practice, inflection point. And again, you have the graph. You can see if there's 1, 2, or none inflection points. Give it a try. Okay, so for inflection point, we take the second derivative. So the first derivative is x squared minus 4. The second derivative is 2x. We set the second derivative equal to 0, divide by 2, divide by 2, x equals 0. But remember, it's an inflection point. So we have 0 comma something. We got to figure out what that something is. So we go to the table, plug in 0, and you get 0, 0. But I cannot emphasize enough, you have the graph. Go check. If I go look at 0, 0, is this where the change happens? Notice it was concave down. And then at that point, it changes to concave up. So you have the graph, right? Verify. If you graph it in the beginning, you can see all the extrema, all the inflection points, x-intercepts, y-intercepts, just by looking at the graph, just by looking at the graph. Okay? Now, I do want to give a few more pictures about absolute and singular, absolute and local. Again, let's practice. In this example, max or min, max, absolute or local. This would be an absolute max. There's no point that's higher, nor will there ever be any point that's higher. That would be an absolute max. We'll talk about that in a little bit. Getting closer. Now, let's look at this picture. We are going to practice this one, but before we do anything, does this graph, x to the 2/3, have an extrema? Where is it? What's the exact point? 0, 0. So before you do any work, you already know the answer is 0, 0. Your job is to find it. So you have the function x to the 2/3, find the extrema. That's all we're doing is extrema, stationary, singular endpoints. And again, you already know the answer. There is an extrema at 0, 0. But again, don't let the derivative or the algebra throw you off. All right, so before we even get started, just by looking at the graph, we knew that there was an extrema here. And by the picture of it, is this a stationary point? No, stationary is top of a mountain, bottom of a valley. Do you see any stationary points at all? There aren't any. What is a sharp corner called? Singular. So we know this is singular and we know where it's at, 0, 0. Do we have any endpoints? No. So there's no stationary, there's one singular, and there's no endpoints. I haven't done a lick of work yet, and I already know that. Okay, if you have the graph. Now, stationary is probably where many of you are stuck. If you take the derivative, you get 2/3 x to the negative 1/3. You set it equal to 0, and you're like, what do I do now? Well, what I always suggest is anytime you have a negative exponent, move it to the bottom, make it a positive exponent, and then you're still stuck. This algebra is going to show up several times. And there's two ways to do the algebra, okay? I'm going to review both of them, and you can choose which one you like. You can either make a proportion, or you can clear the fraction. Either one's fine. The first one is make a proportion. 0 is like 0 over 1. And how do you solve a proportion? You cross multiply. Well, 3x to the 1/3 times 0, what's anything times 0? 0. And what's 2 times 1? So you end up with no variable and 0 equals 2. Does 0 equal 2? No. All of that's to say no solution. Remember, that's possible. You can have a number, multiple answers, you can have all solutions, or you can have no solution. This one has no solution. But again, how do you deal with a variable in the denominator? Proportion is one way. Another way is called clearing the fractions. Clearing the fractions. So basically, if I multiply both sides by the denominator, 3x to the 1/3, 3x to the 1/3, you're just left with 2, right? 3x to the 1/3 divided by 3x to the 1/3 is 1. But I got to do it to the other side. 3x to the 1/3 times 0 is 0. You get the same answer by clearing the fractions, and 2 does not equal 0. Therefore, you have no solution, which bottom line means there's no stationary. And by the picture, there are no stationary points. There's no top of a mountain, bottom of a valley. Then when we look at the derivative, 2/3 x to the negative 1/3, remember, I always like to rewrite it. And you're like, why does he make me rewrite it? Here are the reasons why. If you rewrite it, you know that the x is in the denominator. What number would make this undefined? 0. X 0. X 0. 0 raised to the 1/3 is 0. 0 times 3 is 0. 2 divided by 0 is undefined. So we're going to make a table in a little bit, and we'll plug it in. And then endpoints. Were we given any domain or anything like that? None. So the only point we have is 0. So let's go to the calculator if you want to practice all of it. Go to y equals. We're going to put x raised to the 2/3. Again, be careful. If you need to put parentheses around the 2/3, please do. And then, as you told me in the beginning, when you plug in 0, you get 0. So you knew that before we even got started, that you have 0, 0. But now the only thing we're adding today is this a max or a min? It's a min. And is it a local or absolute? It's an absolute min. That's the only thing we're adding today. But where are we struggling? Algebra, 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 derivative, derivative, derivative. And then when you have to graph it, the graph. Okay, so to kind of work on this a little bit more, then we have two big examples that I want to get to. Just to show you some pictures, again, this would be an absolute max. This would be an absolute min. Why it is the lowest point. This one would be a local max. This would be nothing. This would be nothing because they're along the way. This would be a what? Local min. Okay, so we're just going to, at the end, call them local or absolute. So just kind of giving you a little practice, seeing it. Here's another one. Now they basically took some parts of it off. So this, again, only what you see in the bold line. This would be an absolute max. This would be an absolute min. This would be a what? A local max. Why? You have to walk up to it, right? This would be a local min. Okay, and again, they just kind of cut it in different places. I think you kind of get the idea. But the question I was asked before, I think you're okay on this one. Again, this would be an absolute. This would be an absolute. This would be a local min. Okay, and again, just the more you see, the better you get at it. But the question I was asked was, can you have more than one? And the answer is yes. If you have 2 points and they're both the highest, you can have more than one absolute max, and you can have more than one absolute min. But again, they both need to be the highest. They both need to be the lowest. So you can have more than one. You can have more than one. Okay? All of that to say, time to practice. Okay? So we're going to work on this problem, and we're going to focus mainly on extrema. We're just going to focus on extrema. And remember, today's lesson is when you're done, is it a local, is it an absolute, is it a max, or is it a min? So basically, you have the function x to the third minus 6x squared. You are given a domain of -7 to 7. You are not given a graph, so you're going to have to graph it. And you're going to do stationary, singular, endpoints. You're going to graph it, and you're going to label it. Okay? So find extrema. Find extrema. So again, today we're focusing on extrema, and we're focusing on absolute or local. We learned inflection points, x-intercepts, y-intercepts, increasing, we learned all that, but right now we're focusing on extreme. So extrema, stationary, singular, endpoints, make the table, make the graph, we're on our way. Stationary, you take the derivative, 3x squared minus 12x equals 0. Okay, this one is quadratic, so you could use quadratic formula. But I'm going to go ahead and factor out a 3x, which leaves you with x minus 4. Set each piece equal to 0. You get x equals 0. X minus 4 equals 0. Add 4, x equals 4. So we have 2 possible singular points at 0 and 4. And we'll figure out what they are. But again, algebra. Okay? Singular. We look at the derivative. Is there any number that would make this undefined? Anything we could plug in or divide by 0? None. And then endpoints, that's the domain. So we have -7 and 7. So from our work, there are 4 places we need to look. And if we made a mistake, was it the algebra? Was it the derivative? Was it the understanding? From my understanding, most people can know what to do, but the details of little mistakes is what happens. Okay? Now, we're going to go to our calculator, and we're going to plug those numbers in. So we go to y equals, we plug in the original, which is x raised to the third minus 6x squared. We go to the table feature, second graph. We plug in 0, which gets 0, 4, which gives us -32, -7, which gives us -637, and 7, which gives us 49. So we're gonna have to really work our window for this one. So again, in addition to all of that work, you need to know how to make an appropriate window. So we need to check out 0, 0. We need to check out 4, -32. We need to check out -7, -637. And 749. So once we're given a domain, the domain that tells us our x, we have to go from -7 to 7, right? The domain doesn't give us a choice. We know that's where it begins, that's where it ends. Now, the y, we do have a choice, and we're going to have to get some kind of extreme sort of window here because the lowest is -637. So how low should I go? To what? -700, but again, -750 works well. I just want to count by hundreds because I'm lazy. Like that. And then how high should I go if I need to see 49? Probably 100. Okay. Now, some of you are saying, I'm struggling a bit with the window. How do I know if I have an appropriate window? Well, the answer is, can you see all the points? 0, 0. Got it. 4, -32. Got it. -7, -637. Got it. And 749. Got it. If you can easily label all the points, you know you did it correctly. Okay. And then let's go to our calculator. Go to window. Our x is -7 min, x max 7, scale 1s, y minimum -700, y max 100, and I counted by hundreds. And now that I have the graph, I can label everything. So I hit graph. There's your picture, which kind of matches the points. It goes up, goes down, and goes up again. Okay, so we have 1, 2, 3, 4. And now we're going to label each one. We're going to label each one. So what do we have? Absolute, local, max, min at 0, 0. Local, max. What do we have at 4, -32? Local, min. What do we have at -7, -637? That's an absolute min. It's the lowest point in the entire graph, and there's nothing low. And then what do we have at 749? Absolute max. Now, I didn't give you a ton of time, but this was a straightforward one. And if you got it, fantastic. That means you know stationary singular endpoints. Hopefully you're comfortable with the algebra. Hopefully you're comfortable with the graphic. And life is fantastic until I gave you this one. So our last problem for today, bum, bum, bum. And it's not that it's super bad. It's not that it's super hard, but this is going to possibly throw you off. So you now have the function x plus 4/x with the domain of 0 to infinity. You're going to find stationary singular endpoints. You're going to make a table. You're going to make a graph, and you're going to do all the same stuff. Let's see how you do. So imagine being stuck on even just taking the derivative. Like, how do I take the derivative of this? Well, what I would do first is I would rewrite it. This is x plus, this is 4/x to the 1. When that goes up, it's 4x to the -1. That'd be my first step. Then you take the derivative, make sure you did it correctly. It's 1 minus 4x to the -2 and set it equal to 0. then if we're stuck here, that's going to be the tough part, right? So what would I recommend? Couple things. Number one, I would write this as 1 minus 4 over x squared set equal to 0. Then there are two ways. I'm not going to do both ways all the time, but I'll do both ways now. One is with proportions, one is with clearing the fractions. Both of them are great. You choose whichever you want. It's good to know both. So if you want to solve it with proportions, you have 1 minus 4 over x squared equal to 0. I need to make a proportion. So if I add 4 over x squared, add 4 over x squared, you end up with 1 equals 4 over x squared. And 1 is 1 over 1. You've now created a proportion. 1 times x squared is x squared. 1 times 4 is 4. X squared equals 4. So x equals plus or minus 2. That's one way you could have dealt with it. Another way you could have dealt with it is when you had 1 minus 4 over x squared equals to 0, the problem is the x squared on the bottom. So if I multiply everything, both sides, by x squared to get rid of the x squared times 1, you get x squared. X squared over x squared, you're left with a minus 4. X squared times 0 is 0. That's called clearing the fractions. Add 4, add 4. X squared equals 4. X equals plus or minus 2. That is the algebra that's going to hold us back on certain problems. You have two ways of doing it. Both of them are great. You get to decide if you want to do proportions or clearing the fractions. They're both good. They're both good. Okay, so again, that's going to show up. And if you're like, no, it's not, number 2 on the test will be one of these. Number 2 will be this. Okay, you're going to see that algebra again. Okay, now singular, we look at the derivative, which is 1 minus 4 over x squared. What number would make this undefined? 0. So we got 0, we got negative and positive 2. Endpoints is from the domain. What did the domain tell us? 0 to infinity. We can't really use infinity, but we can use 0. So after working these out, we have negative 2, 2, and 0. And I'm going to pause there and give you time to get caught up and ask questions. But that is what we should be able to do. But don't let that algebra slow you down. Don't let the algebra slow you down. Okay, finish it from there, graph it, and finish it up. So I'm not sure if anybody noticed something, but we'll see if anybody caught something. Well, I'm going to go to the table. I'm going to go to the calculator. I'm going to go to y equals. I'm going to plug in the original. I'll even write it like the original. X plus parenthesis 4 divided by x. If you put x, 4x to the negative 1, same thing. And then when you plug in negative 2, 2, and 0, negative 2, 2, and 0, you get negative 4, 4, and error. Negative 4, 4, and error. But what does error really mean? Undefined. And if it is undefined, is that going to be a max or a min? It's going to be nothing. Anybody notice anything else before I tell you? What do you notice? Yeah. Remember I said that it has to be between 0 and infinity. So negative 2 is not an option as well because it doesn't exist. It's not in the domain. So those 2 points are gone. The only one we have is 2 comma 4. 2 comma 4. So again, remember the domain and remember undefined. There's something going on there, but it's not going to be a max or a min. But there's something going on and we'll see it in a minute. So since my domain is 0 to infinity, I can't go to 0 to forever. I know I need to see 2. So how far should we go? 0 to 10, 3, 4, all of those is great. I'll do 5. I'll kind of compromise based on what you guys said. And then the y, they don't give us anything at all, but I need to see 4. So what should we do for the y? From what to what? 0 to 10. Sure. And again, we can tweak this, we can change it, all we need to, no problem. Okay, but the bottom line is, can I clearly see 2, 4? And I can. I can clearly see 2, 4. Okay, so I go to my calculator, go to window. Remember, we can change this if needed, but I'm going to go from 0 to 5, counting by ones, 0 to 10, counting by ones. And if it looks good, then we're good. If not, we can always tweak it. Press graph. There's the graph. We have 1 point. And what is that point? Absolute or local? Absolute min. We have an absolute min at 2, 4. And again, issues are going to happen with the stationary, with the graphing, all these little things you can see. And if you're like, wow, this is so much harder, it's the same thing, just a little bit more algebra. Now, we're going to finish this off because right now, all of you are telling me, I got this, I got this. Okay. So the very last question, x plus 4 over x, find inflection points. Find inflection points. And I'll remind you, look at the graph. Look at the graph. Okay? Find the inflection point. Do the work, but don't forget to look at the graph. So we're going to find the inflection point. The very first thing I would do is rewrite it just like we did before, x plus 4x to the -1. That's going to help me take the derivative. But let me hold off a second. Look at the graph. This is the graph. We can see the graph. Where does it change from concave up to concave down? It doesn't. The entire thing is a happy face. The entire thing is concave up. It never changes from concave up to concave down. So are there any inflection points? There are none. There's only one extrema. There's no singular. There's no, the endpoint we had 0. And what happened here is we had an asymptote. That's why we got undefined. So I already know there's no answer. Well, let's still do the work, but we already know there's no answer. So if you take the first derivative, that's 1 minus 4x to the -2. If you take the second derivative, you get what? 8x to the -3. We set that equal to 0. 8x to the -3 equal to 0. I'm going to call that 8 over x cubed equals 0. Now, you have 2 options. You have proportion. You have clearing the fraction. Whatever one you want to do. If you do proportion, x cubed times 0 is 0. 8 times 1 is 8. If you did clearing the fraction, multiply everything by x to the 3rd, you get 8 equals 0. Does 8 equal 0? So what do you get? Which is what we did earlier today. So this is nothing new. This is not, I forgot algebra. We had this same issue on a previous problem. And if you're trying to find an answer, there is no answer. And to make you feel better, there's no going from concave up to concave down. You have the graph to answer all of your questions. Okay? And that leaves us with only one section left, which will be the word problem.